Hello and welcome to today's lesson on zeros of polynomial functions. Now to recall, a zero is a value, again like x equals some number, where f of x equals 0. So again, we are finding a number that we can substitute into our polynomial and evaluate to make that polynomial equal to 0. Graphically speaking, a 0 is the x-intercept, or one of the x-intercepts of a polynomial function. One way we can find these zeros is called the rational zero test. Now, before we talk about the rational zero test, I want to talk about the polynomial that we're going to look at. So this polynomial we call f of x. Notice that there are multiple terms here. Each term has a coefficient, a sub n minus 1, and so on, until we get to a sub 2, a sub 1, a sub 0. These coefficients must all be integers. Now also we can look at our x pieces of each term, x to the n minus 1, and so on until x squared x, and then no more x, so this is a constant term. This polynomial is written in descending order with our degrees, so this is the nth degree and less, and so on and so forth. Okay, so again, looking at this polynomial, the rational zero test says if the polynomial f of x has only integer coefficients, which we said, these a sub n's and so on, then every blank zero of f has a certain form. Now, the form of all of these zeros is going to be a rational number p over q, and we write that in lowest terms. Now, this blank is a very important piece of this. It's not that every zero that we can find or every x-intercept works for this one. It is specifically only the rational zeros that will work here. And when we say rational, we mean we can find them in, again, a fractional form like this, integer over integer. Because it's only the rationals, you won't find irrational numbers like root 2 or something like that. So again, we can find all of the rational zeros of this polynomial, and they will all be in this form, where again we have p and q, and we know that p is a factor of the constant term. That constant term is right here. Remember, that is our a sub 0. And q, this denominator, is a factor of the leading coefficient, this a sub n. So again, using this polynomial, our leading coefficient, our constant term at the end, every single one of our rational zeros will have this form. Now we will use this to try out or find some actual zeros on polynomials in our examples. Before we go over examples, we're going to find out the steps for using this rational zero test. The first step is you're going to list all of the factors, we call them p, of the constant term. So we look at that last term, the constant term, and figure out all of its possible factors, both positive and negative. Step 2, we will do the same thing, list the factors q of that leading coefficient. Find that front integer, the coefficient of our first term, find all of its positive and negative factors. We call those q. Next, we will write all the possible ratios p over q. These will then be the possible rational zeros, the ones we could possibly create there. And lastly, we will test each one to find out which ones of those will actually be the rational zeros. Again, by testing them, we mean we are going to substitute it into the polynomial, evaluate it to see if it actually comes out as 0. So let's try our first example using these steps. Our question is, find all rational zeros of the polynomial function f of x equals x cubed plus 4x squared plus x minus 6. So we're just going to go right down the list with all of our steps. First, list p, and remember, these are all of the factors of our constant term, negative 6. Now, negative 6 has factors positive negative 1, positive negative 2, positive negative 3, and positive and negative 6. And one thing I should have pointed out before, again, notice all of these coefficients are in fact integers. Moving on to number 2, list q. Again, all of the positive and negative integer factors of this coefficient. Now, again, it's not written out here, but there's kind of that hidden coefficient of 1 here. Here's our integer 1. If we need the list of all of those possible factors, it's actually a rather short list. It's only positive and negative 1. Step 3, we're going to write all of the possible ratios, P over Q. In this case then, our numerator could be 8 possible things, positive negative 1, positive negative 2, positive negative 3, and positive or negative 6. Our denominator can really only be 2 things, positive or negative 1. If we check all of these as a ratio, put each of these numerators over each of these possible denominators, here are the 8 possible rational numbers then that we could get. Positive negative 1, positive negative 2, positive negative 3, and positive negative 6. Now that we know these are the only possible rational zeros we could get, we are going to test each one, and we will show that on the next slide. So again, using this polynomial, we are going to test each one of them. So instead of f of x, we're going to use f of negative 1, f of positive 1, positive negative 2, positive negative 3, and positive negative 6. So when we test negative 1, again, we are substituting that into our polynomial function up here. And when we substitute it in and evaluate, we'll figure out that this one comes out to negative 4. That tells us negative 1 is not actually one of our zeros. So we move on. We try it with positive 1. We plug it in. And when we evaluate it, we get 0. That tells us, yes, this one is one of our rational roots, or our rational zeros. This one works out. We do the same with negative 2. Plug it in. Evaluate it. This one also comes out as a 0. So that tells us here's one of our rational zeros. We plug in 2. Again, we evaluate it, and we get 20. That tells us that one does not work. Next, we plug in negative 3. Negative 3 into each spot, evaluate it, gives us a 0. So we have found 3 rational zeros. Next, we try positive 3. Evaluate it, it doesn't work. Next, we try negative 6. Plug it in and evaluate it, it does not work. Lastly, we try positive 6. Plug it in and evaluate it, it does not work. Now, as we look back at our polynomial function, we notice this is a cubic or a degree 3 polynomial, which tells us at most there will be 3 zeros, and we found all of them, 1, 2, and 3, which tells us this only has the rational roots or the rational zeros. So we can say then the rational zeros for this function are x equals 1, we found that here, x equals negative 2, we found that here, and x equals negative 3. We found that right here. So again, this concludes our first example. Let's look at another example though. Write the following polynomial as a product of factors that are irreducible over the rationals. So again, in this polynomial, we have f of x equals x to the 4th minus 4x squared plus 3. Notice this one is a 4th degree polynomial, so there are 4 possible roots or 4 possible zeros for this polynomial. We're going to do the same things we did before to help us find the rational roots, but then we're going to use division, either long or synthetic, to divide those factors out and leave us with a either a quadratic or a cubic, or again something that would only give us irrational zeros, some other factor then, and we can work from there. So again, step number 1, list all of your possible p factors. So we look at the last term, this constant term 3, and we know that the only possible factors are positive negative 1 and positive negative 3. Next, we look at our leading coefficient, which again, kind of a hidden 1. If it doesn't have that coefficient in front of it, it's an implied 1. So again, positive and negative 1. Next, we write out the possible ratios, P over Q, which means, again, positive negative 1 or positive negative 3 over positive or negative 1. Again, if we were to write out all those possibilities, there would be 4 different rational zeros that are possible, positive or negative 1 or positive or negative 3. Lastly, we test them. And again, we will show this on the next slide. We are still going to use this polynomial, but again, we are going to test or substitute in these values, negative 1, positive 1, negative 3, positive 3. Each time, again, all we are doing is just substituting it into our polynomial, and evaluating to see what we get. Now, when we evaluate, we only found two possible rational roots, -1 and +1. So the polynomial has rational roots or rational zeros at x equals -1 and x equals 1. This tells us then that it has the factors x minus 1, and this one is actually because of this 0, and x plus 1. That was actually because of this 0 here. So what we can do with that information next is we will use division, either long division or synthetic division, to find that last possible factor. And again, we will do that on the next slide. Again, using this polynomial and using the fact that we know these are already factors, x minus 1 and x plus 1. We will first use division, and I'm going to do it as synthetic division, to figure out other terms that we can pull out. So because of this x minus 1, I put +1 here. Because of these coefficients, 1, 0 in front of the cubic piece, -4, 0 in front of the linear piece, and 3 is the constant. I put those coefficients here, and we continue with our synthetic division. Bring down our first number. 1 times 1 makes 1. Put these two together and make 1 again. 1 times 1 is again 1. Add these two together and we get -3. 1 times -3 makes -3. Again, combine these two. 0, -3 makes another -3. 1 times -3 makes -3. And combine these two or add them together and we get 0. Again, this one being our remainder at the end. With that remainder of 0, that tells us that it divides out evenly. So we can say then, instead of using this as our polynomial, we can divide it out to say, well, we know we have this x minus 1. We divide it out here. And here are the coefficients then that we are left with. So 1x cubed plus 1x squared minus 3x minus 3. We also know we have this factor. So we're going to divide that one out as well in our next steps. Take out the -1 here and go through the exact same process or steps as before. Drop down the 1, and -1 times 1 is -1. Add these together to get 0. -1 times 0 is 0. Add these together to get -3. -1 times -3 is +3. -3 plus +3 gives us, again, a remainder of 0. So that means we know after we divide this out, again, here was our term from before, or our factor from before. Here was our next factor that we divided out, and we are left with a quadratic piece, x squared minus 3. Now we know that this will only have irrational roots. In fact, the roots will be positive and negative square root of 3, and we just needed it to be irreducible over the rationals. So the zeros that it gives us, positive and -1, and then because of this quadratic factor, positive and negative root 3. But again, we were just writing it as these factors. Okay, so that follows up on our two examples. Now lastly, in the past, students have asked some interesting questions such as, what if the leading coefficient was some other integer besides 1? This is possible. In our examples, we only saw examples where our leading coefficient was 1. It is possible that it is other things besides 1. And I'm going to leave you with the fact that you may have fractions as your rational zeros. So as you try your exercises or your homework problems out, notice you can have fractions as zeros. That will happen when this is anything else other than 1. You will see that in your examples. Also, students have asked, what if the constant term at the end of the polynomial is 0? Now, I'm not going to tell you exactly what happens then, but I am going to ask you to think about the idea of the y-intercept. If your constant term is 0, what does that tell you about the y-intercept? Think about that, and think about, again, looking back at this example where we used long division or synthetic division to help simplify our polynomials. And that'll wrap it up for our lesson on the rational zero test.